Hello, good evening to everyone. This video is about our last challenge number 2 for the part 3, wherein we conducted an experiment uh, with the use of our very faulty omatic blower from the lab. So here is a simple sketch, and we're just gonna explain and break down our energy balance for this one. Okay, so let's take a look at our blower. So we have here our inlet, and this is gonna be our outlet. Okay, uh, just setting our agreements with the machine. So this is where the air will come in, and this is the air will come out. So what factors should we consider with the air coming in? So first, we're considering the mass rate, so mass flow rate, so m dot n, temperature t dot n, and its velocity vn. Also for the outlet, so what's going to be coming out of our blower? So it's a hot air. Well, it's not just hot air, it's a hot air coming out at such high velocity. So we still have that mass flow rate out, the temperature out, which is now much more hotter, and our velocity out. Okay, now since we're only on our table, we're only measuring the temperature, the diameter of the anemometer, the dryer. We did not measure anything about how hot the blower has been, like the plastic component itself. So we're just going to be considering, for the sake of math, we're going to be considering our blower as an adiabatic process. So it means that nothing will be transferred to the plastic. We'll just be measuring the temperature of the air coming out. Let's say, for example, that's our system boundary or dotted line. And this one is also a control volume. Okay, so this is a control volume. In an open system like this, mass is constantly crossing from our inlet to our outlet. They're continuously crossing our boundary. So this is my boundary. It's because it's at a steady state. The mass balance is simple. So what we're gonna have is what comes in, MIN, oh, it's shaking, will also come out. So equals to m that out. Okay, every molecule in the fan sucks, and at the back has to be blasted out in the front. We are not creating air, we are just borrowing from the room. We're just making it hot, we're making it spicy, then we're gonna blow it out. Okay, now we have here our mother formula. Zoom it in, here we go. So this is our mother. I just like to call this the mother formula. If USA has its MOAB, mother of all bombs, then we have here our mother of all formula. So let's call her MOAF. So this is our MOAF. So, oh, the police. So this is a steady flow energy equation. So it looks too long, looks too complicated for some, even for me at the start. But for a hair dryer, we're just gonna be assessing our formula and cancel out things that we don't need. So first of all, what's the first thing that is obviously not needed in this equation or in this formula? Okay, first is one, G, Z out, Z in. What does it mean? Well, it's talking about potential energy. The G is the gravity, Z out, and Z in is the difference in height. So we don't need that. We don't need that thing. So I wanna cancel it out. Erase it. Heat loss. As we talked before, we consider that the casing is adiabatic since we are measuring it. We're not measuring its temperature. Is it perfectly adiabatic in real life? No. The plastic gets warm, but the air moves so fast it doesn't have time to lose significant heat to the wall. So we set our Q as 0. So let's write PE is equal to 0. Q is equal to 0. So we're gonna cancel that out now. So aside from that, now we're left with this electricity. So this is our shaft work or electric work. You will see W shaft in our textbooks in our lecture notes. So this is the mechanical energy we use to spin the blades. Spin the blades on the inside of the on the inside of the blower. In our case, we bundle this into our total electrical work, so that's why we're using W elect coming from the wall. So, or the plug, the power handles both the fan motor and the heating coil, so we just use one power in for the term. Next, do you recognize this one? H out minus H in. This is the enthalpy. So, why do we use enthalpy and not just internal energy? Because we're talking about heat. Well, we're gonna think of enthalpy as our bank account of energy. So this is gonna be our bank. Oh, why did I write E? So it's supposedly H. So yeah. Because the air is moving, it's not just about how hot it is. So we have the temperature. It's not only about how hot it is, it's also about the energy needed to push that air along this course of boundary. And what's needed to push the air? We have PV. That's why the formula for enthalpy formula for enthalpy is H is equal to U plus P small v. That one. Energy enthalpy combines both, so it is a total thermal bank balance of our moving liquid. Now, here's the trick. Let's go back to 1. Here's the trick. Can we replace this enthalpy with something else? Well, yes. What we can replace it with is CP CP delta T. Okay? So why? Usually enthalpy depends on temperature and pressure. But for ideal gases, like air, the molecules are so far apart that pressure doesn't really matter. So the energy only cares about our temperature, which is one of the main goals of this experiment. So CP, or specific heat, is our conversion rate. It will tell us exactly how much energy is added for every degree the temperature jumps. So multiply that by our triangle T in here, which is our temperature change, and we have our enthalpy change without ever opening a massive table to consider the P and whatever, blah blah blah. Oh, this is a shortcut. It's a cheat sheet, so don't tell Sir Tim about this. Just kidding. He might be watching this, but yeah. Next, the V2 term. Okay, so last part we have the kinetic energy. So we assume that the air in the room is still, or it is not moving. So we have here this Vn. So we're gonna be considering Vn is almost not exactly 0, but almost 0. Okay, it's almost 0, so we only care about our V2 out. So we're going to be canceling this. Shoot. We're going to use this, and we're going to use this. Okay, now let's go back on our drawing. So this is the motor fan. So this is our heating coil. So this is the inlet and this is the outlet. So this is also, I forgot to draw something else. So let's say this is the power outlet. So there you go. Now just last one warning. So our specific heat and temperature, we measure this in kilojoules, but our velocity is in joules, or the basic default unit for velocity is in joules. Okay, so to add them together, you must divide the velocity term by 2000. So that 2000 accounts for the 1/2 in the formula, and the 1000 needed to convert to kilojoules. If you forget this, your answer will be off by a factor of 8,000. So now let's write our final formula. What we have here is total our work, which is with electricity combined, is equal to mass flow rate. We change our enthalpy to specific heat, so Cp delta T, plus we are not considering the velocity of the air coming in, since we consider the air as still or not moving. So we only have V out, V squared out over, instead of 2, we're going to be writing 2000 with the reason that I said earlier. Okay, so now this is our final balance equation. So your balance equation should be similar to this, or if you have a different way of solving this, then it's fine. So for this one, you might be asking, so we have a fan and we have the coil, so what's the matter with those two? Are we not gonna break it down? Well, we are. So we're just gonna break it down quick. So let's just say this is the work for the fan, and this is the work for the coil. Since we are not computing how much output or how much energy we're spending on the fan and on the coil, we just regarded that we are adding both of these to get these W electricity. So we're just assuming that we are merging them together as a unit power of 1. So there we go. So this is most probably how it's gonna look like in your paper. So before you go, please like and subscribe, and invite your other classmates to watch the video. So yeah, thank you.